Hello. Today we will be talking about the final project that we have done on the article of human body composition by G. Forbes. We have observed the article that talks about a lot of placenta and fetal mass and how it changes over the course of gestation. To start it off, we have mapped out all the points of the given graph that was on the article, and then we decided to plug that into a table and open it under Excel, which has given us the ability to map out the polynomial of the graph. And through that, we have fitted it in a 1 polynomial and a 4-degree polynomial. After which, we were able to plot it out on Desmos using the function that we were given, which then gave us a better fitting of the graph. We have gotten that better fitting due to the fact that since it's a higher degree, it makes up for a lot of error that would be given through a 1-degree polynomial. For table 1, we have taken the points on the graph of the article and put them onto the table. We then converted the weeks into days to make it more accurate for our information.
For part 1, we accumulated all of the data that we found from the original graph given, and we plotted those points and created a graph using Excel, Word Excel sheets, and then we were able to set up our first fetus degree and our second placenta first degree. So for fetus 1 degree figure 1a, after we acquired the particular points for this, we made the graph, and our polynomial is w prime of t 0.059979246 plus 7.56910190056. So we used 10 digits, which were expected of us as we made the calculations. And the fitting for the polynomial degree 1 was really bad because the R value for the fetus was 0.3, which is not close to the acquired data point, which is 1. So the dots were not near the polynomial degree on the line at all. For the placenta first degree figure 2a, we did the same thing. We used the given points. We made the graph, and the w prime of t equaled 0.0015306.122t plus 2.95000000, and that was also an extremely bad R value. The placenta R value was 0.009, which is not close at all to the desired 1, so the dots did not hit the line at all once again. For the next part, we changed the graphs to polynomial 4th degree, and from the results that we saw from both the fetus and the placenta, there were dots that hit the line, yet there were some outliers, but on either graph, a good portion of the dots made hit the line, which was exactly what we needed, which would tell us by inferring that our R value would be at least closer to 1, if not 1, than before. For the fetus fourth degree, figure 1b, the fourth degree was W prime t from the equation shown on the PowerPoint. So this told us that our R value would be a lot better because, as you can see from the line, the polynomial line in the fourth degree, a lot of the dots hit the mark. So this told us that this is a better fitter, like it's a better fit than the linear degree, because the R value for the fetus is 0.7, which is not 1, but it is very close to 1. For the placenta fourth degree, figure 2b, our fourth degree fitted polynomial was W prime of t, and the equation is shown on below the graph. And this is also better fitting because our R value is 0.9, which is extremely close to the acquired 1, and the dots were near the polynomial degree 4 line, which was exactly what we wanted. For the next part, for part 3, we had to find the inflection points, and using Desmos, we were able to calculate it. So the inflection points for figure 3, fetal growth in grams per weeks, it was double prime. And for the placenta growth for figure 4, it was grams per weeks, double prime also. And by us using Desmos, we were able to graphically see the inflection points and where the change was with the fetus and with the placenta. And the next 2 slides are going to show where exactly the inflection points are to the best of our ability to maneuver Desmos in a way where we could enlarge the graph so that it is able to clearly be shown of both the fetal and the placental growth. So for the inflection points for figure 3 fetal growth, grams per week, double